Today we're going to be learning about Coulomb's law, which is going to quantify the charge model that we talked about last time. To recap from last time, our charge model said that we have positive and negative charges, that like charges repel and opposites attract, and that force decreases over distance. So today we're going to look at that force decreasing over distance using Coulomb's law, which is an equation to quantify the relationship between force, charge, and distance. So here it is, Coulomb's law. We've got force equals 1 over 4 pi epsilon naught times the absolute value of charge 1 times the absolute value of charge 2 over r squared. Now something important here to note is that Q1 and Q2 have absolute value symbols. So right there, absolute value. And that's because when we talk about positive and negative charges, there's really no reason that one is positive and one is negative other than to state that they're opposite. It's not really a mathematical thing, it's more of just a differentiation tool. So when we actually are doing the math, we have this force vector, because force is a vector. So the force vector has a direction that is positive or negative or some combination if we're in 2 dimensions. And that direction is not going to be determined by the positive or negative value of this equation. It's going to be determined by the relationship between the charges themselves. So we're not going to look at that mathematically. We're going to look at that in a more qualitative manner. So we'll use this equation to find the magnitude, but we'll actually look at the diagram to find the direction. Coulomb's law can also be written this way. Force equals K Q1 Q2 over r squared, and the difference is that we have a K here instead of a 1 over 4 pi epsilon naught. So, lazy people get tired of writing 1 over 4 pi epsilon naught or saying 1 over 4 pi epsilon naught. So we can just abbreviate that as a K. It's the same value as 1 over 4 pi epsilon naught on your formula chart. It'll say K equals 1 over 4 pi epsilon naught equals 9.0 times 10 to the 9th newtons times meters squared divided by coulombs squared. It's simply a constant. And the shortened way of writing it is K, but you may also see it some places as 1 over 4 pi epsilon naught. That epsilon naught is the permittivity of free space, I believe. So it's just how charge works in a vacuum as opposed to somewhere with air. Air will have a different constant, and it would change this a little. But that's beyond the scope of this class, and we're not going to worry about it. We're just going to pretend we're working in a vacuum. So don't be scared if you see 1 over 4 pi epsilon naught or if you see K. They just mean the same thing. You can write it either way as long as you use the correct constant and you come up with the right value. A couple of things to note here. Coulomb's law only applies to point charges. So a point charge is something that doesn't have a charge distribution. All of its charge is concentrated at one point. Now, this doesn't really happen in the real world, but again, for the scope of this class, we're going to assume things are point charges, and this works well when the size of the object is a lot smaller than the distance between the charges that you're trying to evaluate. So we can approximate things as point charges reasonably well, so we don't have to worry about it. Another thing to note is that Coulomb's law is consistent with Newton's third law. So Newton's third law says whatever force one object exerts on another, the second object exerts back equal and opposite. So it's an equal and opposite force. And you can see that mathematically with Coulomb's law, because if you switch Q1 and Q2 in their spots, it's just the commutative property of multiplication. So it doesn't really matter, and you're going to get the same thing either way. And then when you evaluate it qualitatively for the direction of the force, it's going to be opposite. And we'll see that here in a minute. But Coulomb's law is consistent with Newton's third law. And the last little thing before we get on with practice is that forces can be superimposed. So superimposed is usually used with waves, but it just means we can add them together on top of each other. So if you've got a charge that's feeling a bunch of different forces from other charges, you can just add up their vectors. Now that can be a little tricky, especially in 2 dimensions. You've got to know pretty solidly how to work with vectors, how to add vectors, all that jazz, which we will get into. But if your vector skills are not strong, it's something you are really going to need to brush up on for this topic. All right, so we're going to look at a few kind of conceptual problems before we move into some actual math, just to kind of work our brains out a bit. This one says the charge of sphere 2 is twice that of sphere 1. Which vector shows the force of 2 on 1? So you can see the charges are represented there. There's 2 positives in charge 2 and 1 positive there. So these are both positive, which means they're going to repel. So immediately we can mark out D and E, because D and E would mean 1 was moving towards 2, and we know from the charge model that that is incorrect. So now what's left is to choose the size of the vector, the magnitude of the force. And we have something to compare it to. We have this force vector right there. So what Newton's third law says, that we kind of just talked about a little bit, is that force of 2 on 1 equals negative force of 1 on 2. So they're in opposite directions, but they're the same magnitude. So the force of 1 on 2 is this arrow length. And the force of 2 on 1 has to equal that in magnitude and be opposite in direction, which is choice B there, because B is the same length as this one. So really here we don't even have to apply Coulomb's law. We're just looking at Newton's third law and kind of using our brains a bit. And there's your answer. Use Newton's third law. All right, next question. The charge of sphere 2 is twice that of sphere 1. Which vector below shows the force of 1 on 2 if the distance between the spheres is reduced to r over 2? All right, so we can think about this mathematically using Coulomb's law. Force equals K Q1, Q2. These are absolute values, but I'm not going to write it. Over r squared. All right, and we got to make the little force a vector. Okay, so we can take charges if we want to. We can do Q1 times 2 Q2. We could make up charges for them. We could say 1 is 1, 1 is 2. But we don't really have to do that. What we have to look at is our r squared down here, okay? So we're going to look at how the force is going to change if instead of r squared, we have a reduced distance of r over 2 squared. So this is our initial force. Our new force is going to be, I'm going to make this a little bit smaller. Our new force is going to be force equals K, same Q1 and Q2, but now it's over r over 2 squared. And r over 2 squared is the same as r over 4. So I'm going to erase that and put r over 4. Or sorry, r squared over 4. R squared over 4. Now, if we work with the vinculums there, Pipak's favorite word, we're going to move that 4 up. If you don't understand algebraically why that works, then email me or something. So we get 4 K Q1 Q2 over r squared, which is a factor of 4 larger than that one. So our answer here is going to be that it is much larger than before. It should be 4 times as large. And I know this is a little bit misleading of a picture. If you take that distance and you multiply by 4, it is significantly bigger than that one. So the real answer here is none of the above. And there we go. At half the distance, the force is 4 times as large. That question might be coming to a homework near you. Next up, which of the 3 right-hand charges experiences the largest force? Okay, so the right-hand charges are these guys. Okay, so that's the ones we're looking at. Which one experiences the largest force? Okay, so let's evaluate this. This one here is a force of K big Q times little q over regular r squared. Cool, that's the force. Now this next one has an increased distance and a doubled charge on one side. So it's going to have a force of K times big Q times 2 little q over r squared. So now r is 2r squared. And if we algebra that out, we'll get force equals 2kq over 2r. Quantity squared is 4r squared. 2 over 4 is 1 over 2. So we end up with that this one is kq over 2r squared, which is half of the first one. You've got a coefficient of a half there. So the second one is experiencing half the force of the first one. Now we'll go down and look at the third one. I'll do it in green. Force equals K, big Q, 4 little q, over 2r quantity squared. So that is force equals 4kq little q over, if you do 2r quantity squared, you still get 4r squared. 4 over 4 is 1, and that becomes kq over r squared, which is the same as the first one. So 1 and 3 are going to be the same. And that answer choice is E. Q and 4Q are tied. And there you have it. All right, next up. In each of the following cases, an identical small positive charge is placed at the black dot, in which case is the force on the small charge the largest. Okay, so we've got several options. Now, generally, the ones we want to look at are the closest because distance is what matters most because it's got that r squared. So we're wanting to look for something that is the closest. Now, we're also going to have to look at the charge because we've got some things with similar radiuses or radii, whatever. So the two we can narrow down to first are the ones that are closest together, and that is A and C. Okay, they're the same distance. Now, the other thing we have to look at is the magnitude of the charge that is attracting or repelling it. In this case, it's repelling because it's positive. So we got to look at the charge of the other point charge. We've got a Q and a 2Q. Now here, we want a bigger charge at a smaller radius, so the answer is going to be C. Cool beans. Look, we did it, Mom. All right, I promise there's not too many more of these. I think just 2 more after this one, maybe 3. In each of the following cases, an identical small positive charge is placed at the black dot, in which case is the force on the small charge the largest. All charges shown are of equal magnitude. Okay, so we're going to draw some force vectors here. All right, I'm going to do that in, let's say, blue. Okay, so on this first one, we need to note that we've got a positive charge on each black dot, positive charge. So this positive charge is going to repel it, and this one's going to pull it. Okay, this negative, because negative pulls on the positive. So we've got 2 forces going in the same direction, and that's going to be a large vector, twice as big as the small ones. Okay, so that's pretty big. Next up, we've got a negative pulling on the positive, okay, and a positive pushing, okay. But I don't think the positive is pushing super hard because it's further away, so it's going to have a little arrow. So overall, that's going to be this big arrow, biggish arrow, minus that one, because they're pulling in opposite directions, and it's going to be a smallish arrow. We're going to call it smallish arrow. Okay, next up. This one's repelling, pretty big. This one's repelling, but it's pretty small because it's far away. So that one's going to have a semi-large area that way. Definitely bigger than this one, but smaller than that one. And last but not least, we've got two negative charges that are both pulling. So that one's pulling, this one's pulling. They're balanced, so total force there is going to be 0. All right, so we're looking for the case where the force on the small charge is the largest. That one definitely has to be A, because both charges are equally distant there. They're pretty close, and they're both applying force in the same direction. Cool. All right, next up, which I've said like 4 times now already. Sorry. I'm really not varied with my transitions. Okay, the direction of the force on charge little negative q is what? Okay, so we got to do some more force diagrams. I'm going to do yellow. So we've got some distance here. We're going to call it R. And then we've got another distance here. I'll call it big R because it's larger. Okay, little r and big R. So we're going to look at the force on charge negative q. So to start with, the force from the other negative is going to be to the right, okay? To the right. And then the positive charge, because it is oppositely charged, is going to pull on the little charge. But since it's further away, it's not going to pull as much. So we've got a big force vector pointing to the right, a smaller force vector pointing to the left. The net force is going to be kind of to the right. So that is over here to the right. Yay, we did it. All right, this question looks a little bit confusing because all the answer choices are in the diagram, besides none of these. But anyway, which is the direction of the net force on the charge at the lower left? Okay, so the force diagram is not actually already there. Those are all answer choices. We've got to draw the force diagram ourselves. We're going to do that in blue. Okay, so these are all positive charges, which means they're repelling. We're assuming that these big charges are stationary. So this charge right here is going to push on that one pretty hard this direction, okay? Now this one is going to push pretty hard in the downward direction. And this one's going to push pretty hard in the leftward direction, okay? So I'm going to redraw this over here. We've got a positive charge experiencing these 3 forces. Now, you should just kind of be able to look at the vectors there and say that if you add all of them together, you're going to end up this direction, okay? And if you can't see that, I'll show you exactly how it works. So if I take, oh goodness, can't move things. There we go. So if I take a point charge here and I put 3 forces on it, we got to add those vectors together. And one of the ways you can visually add vectors together is that wherever you start or stop the arrow you just did, you start the next one. So we're going to go to the left first. And then we're going to go down at a 45-degree diagonal, like is in the thing. And then we're going to go down, straight down. And if you look at where you started, first was where you ended, you can draw an arrow, a vector that way. And that's going to be your overall vector. So that's a 45-degree angle away from your initial charge. And that is answer choice B. Cool, got it right. Which we should hope I do, because I'm your physics teacher. Which is the direction of the net force on the charge at the top? We got 4 vector options and none of these. So let's draw our own vectors. I'm going to use yellow because I'm feeling like it. And we'll start by looking at the charge from right here. So positive charge and a positive charge are going to repel. So this Q is going to push that direction, and it follows obviously the line between the two. So it's going to push it away that direction. And the negative one, let's see, I'll do this one in blue. The negative one pulls, and it pulls it in its direction. So we've got two forces going like that, and they're at about the same radius, so they're about the same magnitude. So when you got two vectors like that, that look kind of balanced, one's going up and one's going down, their y components are going to cancel, and we're just going to have two x components. So the answer is going to be D. If you did not follow that, I'm going to draw the diagram over here. I've got a positive charge, and to add the two forces together, to superimpose them, take one, draw it upwards like that, take the other one, start it. It's like as if we were taking this arrow and moving it. Draw it down from where you ended the previous arrow, and then you draw your final vector from your starting point to your ending point. That's going to be straight to the right. So our answer is D. Oops, forgot to put the final answer in for that one, but it's okay. I did get it right. I went back and checked, just, to make sure. All right, so that's pretty much how kind of qualitatively things work. You can use reasoning. You can use some geometric vector addition, but we're about to get into the cold hard math. And part of the cold hard math that you have to know how to do is vector addition, which was the most missed section of our pretest, was vectors and scalars, which I figured you would have learned in mechanics, but we're gonna do some brush up. So the process for vector addition is that you have to start with a coordinate system. Now, most of the times, the coordinate system is obvious or it's already written for you, but you do have to make sure there is one. Otherwise, you don't know how to break down your vector into components. It's hard to break something into x and y components if you don't have an x and a y. So first thing you got to do is define a coordinate system. Second thing you got to do is break down the vectors into x and y components. So if you don't know what that means, I'll draw a quick little diagram. This is my coordinate system, and this blue thing is going to be my vector that I make up. Okay, breaking it down into x and y components means you figure out how far it went in the x direction and how far it went in the y direction. Now, if you have the endpoint, this is super easy because it's just the x and the y coordinates. So that's pretty easy. Sometimes it's harder. Sometimes you have to do a little trick. But you have to break the vectors down into their x and y components based on the coordinate system that you defined. So there are usually clever ways to define them, so you have to do less work. And lastly, when you're adding vectors, you have to take the x components, add them together, and the y components, add them together, and that'll tell you the x and y components of your final vector. And if you need to, you can, figure out the length from there, figure out the angle, whatever you need for that question. But that's how you do vector addition. If you need a lot more help on vector addition, which is something that should be pretty standard at this point, please let me know, and I'll figure out some way to teach you. All right, so for example, we're going to look at some vectors here, and I definitely forgot to put coordinates in this slide. So instead of fixing that right now, I'll just assign some coordinates. We're going to say point C is 2, 4. Point D is 4, -3. And B is some weird coordinate that we don't know, but we have an angle and we have a radius. So what we need to do is add together vectors B, C, and D. So we're going to find B plus C plus D. Fun time. Okay, now I need to make this smaller so I can do a little bit of math over on the side. And when I say a little bit, I mean a lot of it. So we're going to look first at vector B, okay? Vector B. So the things we know about vector B are that it's got this 23.8 degree angle from the x-axis, the negative x-axis, and it's got a radius of 4.2. So what we need to find is how far it goes in the x direction, how far it goes in the y direction. So we need to know the sides of this right triangle, which you can do with trig. Okay, so we should know SOHCAHTOA sine of theta, theta is an angle, equals opposite over hypotenuse, cosine theta equals adjacent over hypotenuse, and tangent theta equals, oh gosh, opposite over adjacent. Okay, if you don't have these down pat, you really need to. It's, especially if you're going to be an engineer or a physicist or something that uses math, you have got to know how to do vector addition and right triangle trig. So if you don't know these, learn them, study them, get flashcards, something. All right, so let's look for bx. This is the notation we use. This is the x component of the b vector. So the x component is on this side, the horizontal direction, which is adjacent to the angle, and we have the hypotenuse. So we're going to use cosine of theta equals adjacent over hypotenuse. And I'm going to actually put in theta there. So let's erase out this theta and put in 23.8. Sorry, having to erase things. 23.8, and we are in degrees, so if you're using a calculator, gotta make sure you're using degrees. Cosine of 23.8 degrees equals adjacent over hypotenuse. Adjacent over hypotenuse. So the adjacent here is b sub x, the x component of vector b, and divide that by the hypotenuse, which is 4.2. Okay, so you get b sub x equals 4.2 times cosine 23.8 degrees. I know I am skipping some algebra steps, and that's because I assume at this point you should know very quickly how to do this algebra. If that's something you struggle with and you need me to slow down in my algebra, please email me or something and let me know, so in future videos I can go a little bit more step by step. All right, moving on. So for by, it's the same process, except now we're not looking for the adjacent, we're looking for the opposite. So that's going to be sine opposite over hypotenuse. So you get sine of 23.8 degrees equals opposite over hypotenuse. Multiply it out, get 4.2 times sine of 23.8. Right? So I'm going to math those out real quick. All right, when you math out for this top one, you get 3.843. And for the bottom one, you get 1.695. All right, now in all of that calculation, it's super easy to get caught up in finding the numbers. And the numbers are important, but something you can never, ever, ever forget with vectors is their direction, okay? So we've gotten lengths for the x and the y, but both the x and the y are in the negative direction. So you have to make sure you include the negative with their components, or when you add it all up, it's just going to be super wrong. I actually know that because the first time I recorded this video, I did it wrong. And I was like, wow, that is really not the right answer. How did I mess up? And it's because I forgot both those negatives. So I'm going to erase all the work and just leave the numbers. All right. So the next two are super easy, but people get confused because they get used to doing the trig all the time and they forget that sometimes you can just think it out. So we're going to look at C. We're going to do this one in blue. So C is a vector from 0, 0 to 2, 4. Now, it's super, super easy to figure out the x and y components of this because they gave you the x and y coordinates, okay? So, since the x coordinate's 2, I just went over 2, Y coordinate's 4, it went up 4, and you get that your CX component is just 2, and your CY component is simply 4. Super duper easy. D is a little bit trickier though, and that's because it doesn't start at the origin. It starts way out here and goes back towards the origin. Okay, so its x has a length of 4, which is its x coordinate, but it's headed backwards. So its x component, dx, is going to be -4 because it's going back the other direction. And even though the coordinate for y is -3, it's actually going up 3 on its journey. So dy is going to be +3. So vectors can be kind of tricky because you have to be really, really careful about the signs and the direction that it's going, because that's the whole point of a vector, is that it has direction and you're using those directions to calculate. So now all that's left, since we have the components, is to add those up. I'm gonna make a little column over here and do that. So for x components, we've got -3.843. We've got +2. And we've got -4. Okay. So that's going to be -5.843. Nice. And then y is 1.695 plus 4 plus 3. Oh, except that should be -1.695 because that one was headed down. Must have missed the negative when I copied it over. Okay, -1.695 because that was that. 4 and 3. Oh gosh, I don't want to do that. 7 minus 1 is 6. Minus 6.95 is 5.305, something like that. Let me check. Yep, all good. So we have a vector now that has an x component of negative almost 6 and a y component of positive almost 5. So that would look like -5 over here. It's pretty far away. +5 pretty far away. Gonna look something like this. Probably not exactly, but you know, something like. So it's pretty good. Now, if you have a ton of trouble with adding vectors, none of this makes sense to you, you don't know what trig is, you don't know what vectors are, please email me. This may not be the right class for you. But if you really are struggling and you need help, please let me know. Okay, so we're finally going to do some actual examples with charges and vectors, combining all of our conceptual knowledge with all of our mathematical knowledge in a beautiful marriage of math and physics. So this first example is one-dimensional, means it's pretty easy. We've got 2 +10 nanocoulomb charged particles that are 2 centimeters apart on the x-axis. So before we go any further, we're going to draw that. Have the x-axis. Here's going to be the origin. This was going to be positive. This is going to be negative. And they are 2 centimeters apart on the x-axis. So we're going to put one at, let's make this +1, one at -1. Oof, that was a bad -1. Let me erase that a little bit. -1. At -1 and 1. So they're 2 centimeters apart on the x-axis. We're going to make sure this is in centimeters. What is the net force on a +1 nanocoulomb charge midway between them? Okay, so we're going to have another charge. I'm going to make this one blue. Right here. Okay, we're finding the net force if a 1 nanocoulomb charge is placed midway between them. Okay, so we've got 2 things to figure out. We've got to figure out the force from the right particle and the force from the left particle. and we need to write down their charges. So the ones that are 2 centimeters apart are both positive 10 nanocoulombs. Now, a clever person could see that these are both positive, so they're going to be exerting the same force in the same or in opposite directions on this middle particle. So the net force is going to be 0. If you can't jump to that conclusion immediately, we will math it out a little bit. Make this smaller. Okay. So I'm going to go ahead and label these as charges 1, 2, and 3, just to help us keep track. So the first thing we're going to look at is the force of charge 1 on charge 2. Okay, and Coulomb's law dictates that that is K Q1 Q2 over R squared. Okay, so just got to plug in some numbers there. The force is K. We're going to leave the constant K. It is 9.0 times 10 to the 9th, but we're not going to substitute it in right now, and we don't really have to for doing these kinds of comparisons. So we've got K, and then Q1 is 10 nanocoulombs. And we use the absolute value. We don't care about the actual sign right now. So 10 nanocoulombs, and the charge on Q2 is positive 1 nanocoulombs. Okay. And we're going to put that with R squared. R is 1 centimeter, which is 0.01 meters. Cool. And really, we should change these nanocoulombs to coulombs because that's the SI unit. So I'm going to do that real quick. A nanocoulomb is 10 to the negative 9th. So we've got 10 times 10 to the negative 9th and 1 times 10 to the negative 9th. Okay. And that is meters squared. All right, so there's our force. K times 10 times 10 to the negative 9th times 1 times 10 to the negative 9th times 0.01 meters squared. Okay, so that's the force of 1 on 2, and you could calculator that out and get an actual number. That's fine, but we don't have to because we're just comparing forces. And then we'll look at the force of charge 3 on 2, which equals K Q3 Q2 over R squared, which is equal to K times the charge of Q3, which is also 10 nanocoulombs, so 10 times 10 to the negative 9th coulombs, times Q2, which is still 1 times 10 to the negative 9th coulombs, over the same radius, 0.01 meters squared. So you don't even have to calculator that out to see these two things are the exact same. And since they're exact same, that means their forces are equal in magnitude. And the last thing we got to look at is the direction. Okay, so we're going to zoom back in. Now, the direction is based on the charge, whether it's positive or negative. And we know that all of these charges are positive, so they're all repulsive. So we're going to have from charge 1 on charge 2, a force pushing it away. And from charge 3 on charge 2, it's also going to be pushing it away. And these two forces we just calculated are equal. So the net force, since they're equal and opposite, is just going to be 0. Okay. Now the next question says, what is the net force if the charged particle on the right is replaced by a negative 10 nanocoulomb charge? So let's look at that. Now the math is going to stay the same because it's still a 10 nanocoulomb charge. That number doesn't change. Now it's just a negative sign. So the forces are still the same magnitude. But what's going to happen now is that instead of repulsive charge here, let's see, got to draw my axis back in. Instead of a repulsive force there, this one, which is now negative, is going to pull. So this one's pushing, this one's pulling, so their forces are going to add together instead of canceling out. So really, what your force will be is 2 times k times 10 times 10 to the negative 9th times 1 times 10 to the negative 9th over 0.01 squared. And really, you should write all of your units in there or whatever. But that's going to be your force. Clear as mud? Hopefully clearer, because we're about to move on to 2 dimensions. All right, this one says 3 charged particles with Q1 equals negative 50 nanocoulombs, Q2 equals positive 50 nanocoulombs, and Q3 equals positive 30 nanocoulombs are placed as shown below. What is the net force on charge Q3 due to the other charges? Okay, so we're going to write in these charges so they're there for reference on our screen. Okay, so Q1 is negative 50 nanocoulombs. Q2 is positive 50 nanocoulombs. And Q3 is positive 30 nanocoulombs. Okay, so we've got to calculate the forces on charge Q3. Okay, so we've got to do 1 and 3 and 2 and 3. Start with 1 and 3 and do that math over here to the side. Okay, so we're looking first for force of 1 on 3, and that is equal to, let's see, K, which we're going to leave as K. Sorry, I wrote that really badly. Got to redo. K times Q1. And Q1 is 50 times 10 to the negative 9th coulombs. 50 times 10 to the negative 9th coulombs. Okay. And something to note is we're not carrying the sign over because this is absolute value, because we're only looking for magnitude. And then Q3 is 30 nanocoulombs. So 30 times 10 to the negative 9th coulombs. If you don't know the prefixes, they are on your formula sheet. Okay, and that's divided by r squared. So we got to know r. Oh, fun, fun. Okay, so r is going to be this distance here, as you can find via the Pythagorean theorem. So it is the square root of 5 squared plus 5 squared, which is 25 plus 25, so 50. That's the square root of 50, and that is in centimeters. So it's going to be the square root of 50 divided by 100 meters, okay? So, and then we got to square that for the bottom. So we'll have square root of 50 over 100 squared. So we have force from force on Q3 from Q1 is K, 50 times 10 to the negative 9th times 30 times 10 to the negative 9th over 50, or square root of 50 squared is 50 over 100 squared is 10,000. So you can figure that out. And then following a similar process, you can get that the force of 2 on 3 equals K 50 times 10 to the negative 9th, because it's 50 nanocoulombs, times 30 nanocoulombs for Q2. Oops. Shouldn't have put nanocoulombs, should have put times 10 to the negative 9th. Running out of space. Okay. Over, it's the same geometric setup, so have the same radius squared. Okay. So we can see our forces here are going to be equal in magnitude. And we're going to look at their directions. So I'm going to erase all this stuff that's over here. That's not the actual magnitude of the charges. Okay. So now we're going to take a quick look at qualitatively what's going to happen based on our charge model. So we've got over here a negative and a positive. Negatives attract positives, so that's going to pull over here. And then on this side, we've got a positive and a positive, so that's going to repel there. And since our forces are equal in magnitude, because these are mathematically equivalent, we should kind of, if you're clever, get to the conclusion that the y components here will cancel out. But we're going to do that mathematically, just so we know. And I'm going to real quick actually calculate this thing out to figure out the numerical force value. And I just realized I've been missing a 0 over here for a while, so forgive me for that. All right, so if you actually calculate it, these are all equal to 0.0027. So I'm going to delete that and rewrite it so we can have some more space. We had the force of 1 on 3 equals 0.0027, and so does the force of 2 on 3, 0.0027. So these forces are equal in magnitude, but they've got some different directions. Now, one of the things that you have to figure out here is what the x and y components of these things are. Now, some people would, a lot of people would, make their coordinate system look like this, with x and y. And that is a valid way to do it, x and y. But that puts both of these things on a 45. Do I really like that? No, because I've got to deal with angles and finding an x and y component for both of them. So instead of doing that, I need a bigger eraser. Let's see if there is one. There is. And it's not really erasing. Oh, it's erasing some things. Okay. Anyway, sorry for that technical difficulty. So instead of making the x and y coordinates like you normally would there, you can make them go this direction, which is super nice, because then your two vectors that you're dealing with lie right along your x and y axis. They only have one component each. So that is super, super easy. And then you would just make this a triangle with 0.0027 as your force, 0.0027 as your force. And you can figure out a right triangle from those very easily. So you go like this. This is going to be your force. And the length is 0.0027 squared times 2 square root of, or you can do special right triangles where you do 0.0027 square root of 2 being your length, and it's pointing off to the left. However, if you don't see that and you have to do all of the components, you'll get the same answer, and we'll see how to do that. So I'm going to go back to what most people would consider the typical coordinate system. I figured out how to make the eraser bigger. With this being x, positive x, this being y, positive y. Okay. So what we can see from this is that this vector is right here, and we got to find the x and y components. We know this is 0.0027. Okay, because there's a force of 0.0027 going along that line. Now I've got to find the x and y components. So something you can do here is you could figure out this angle using geometry. You could say this is a 45-90 right triangle. You could use trig, SOHCAHTOA with 5 centimeters or 5 centimeters to find that that's a 45-degree angle. And that's a totally valid thing to do. And then you could say, I'm going to redraw the triangle. This is the triangle. This is 45 degrees. This is 0.0027. So you would figure out this side and this side using trig. That's a valid way to do it. I'm not going to do that way here because it's a bit longer. I'm going to erase that. What I'm going to do is I'm going to use similar triangles, which is a very good technique for vectors, especially on a coordinate system, where I know we've got this triangle 5, 5, and this is 5 square root of 2 because of 45, 45, 90, or you can calculate it out with Pythagorean theorem, whatever. Either way. And now I know also that I've got the same vector, or vector following a similar triangle. Because it is a similar triangle, even though it doesn't look like it here. So I know this is 0.0027. I can use proportions with, like, in similar triangles in geometry. I can say 5 over 5 square roots of 2 is equal to x over 0.0027. So you do 0.0027 times 5 divided by 5 roots of 2 equals x. And you would get that this is 0.0027 divided by root of 2. Cool. Let me scoot this over again. And you do the same thing for y. You find y with similar triangles. You could say 5, because it's this 5 over 5 root 2 equals y over 0.0027. Same process, multiply, divide, you get 0.0027 over root 2. And that's the x and y components of this vector over here. Okay, so you have 0.0027 over root 2, 0.0027 over root 2. And similarly, you could figure out the x and y components of this one, which are 0.0027 over root 2 and 0.007 over root 2. But what you'll see is that with this top one, this one right here, sorry the screen is getting so messy. It's late, I'm tired. So this one is going in the positive y direction and the negative x direction. And this one is going in the negative direction for both. So you'll have negative 0.0027 over root 2 and positive 0.0027 over root 2 for the y components, but you'll have both negatives for the x component. So the x components are going to combine, these are going to cancel, and you're going to have it just going to the left, and it'll be 0.0054 over root 2 in the negative direction. So I know that was a lot, and there's multiple ways to do it. Sometimes you can find a clever coordinate system that makes it really easy. Sometimes you have to use trig. Sometimes you can use similar triangles, whatever works for you. There's lots of methods to solve it as long as you end up with the same thing. So way back when we did it the first time with the clever coordinate axes, we got 0.0027 root of 2. And this time we got 0.0027 times 2 over root 2. And these are equivalent because you can see if you multiply this one by root 2 over root 2, you'd have square root of 2 times the square root of 2, which is just 2, over root 2, which is equivalent to that. So we got the same answer either way. One of them we had to break into components. The other we got to just use a special right. So there's multiple ways of approaching the problem. Some are going to be easier than others. Okay, and our last example, which I promise is not nearly as brutal. says a small plastic sphere is charged to -10 nanocoulombs, yet again. It is held 1 centimeter above a small glass bead at rest on a table. The bead has a mass of 15 milligrams and a charge of 10 nanocoulombs. Will the glass bead leap up to the plastic sphere? Assume gravitational forces between the beads are negligible. Okay, so got to draw this first. We're going to have a small plastic sphere charged to -10 coulombs. So this is going to be a plastic sphere. -10 nanocoulombs, so times 10 to the -9 coulombs. It is held 1 centimeter above a small glass bead. So here's our small glass bead. This is going to be 1 centimeter, which is 0.01 meters. Small glass bead at rest on a table. Cool. Ignore the little levitation there. The bead has a mass of 15 milligrams, which is times 10 to the -6 kilograms. So 15 times 10 to the -6. Got to use those SI units. And has a charge of 10 nanocoulombs. Positive. That's 10 times 10 to the -9th coulombs. Assume gravitational forces between the two beads are negligible. So it's going to make our lives a little bit easier. So we're looking for two things. We're looking to see what the bead is going to do, which is based on the forces, and there's two forces. There is a force in the upwards direction that's caused by the attraction between a negative and a positive. So there's going to be some force in the upwards direction. But there's also force in the downwards direction because we live in a world with gravity. And that is going to be mg. And that'll be super easy to calculate. We'll do it last. We're going to start with the force going up, the electric force, with Coulomb's law. Coulomb's law says force equals K Q1 Q2 over R squared. And that's pretty straightforward here. Stick with K. K is 9 times 10 to the 9th, whatever the units are. Q1, so let's call this one 1 and this one 2. Q1 is 10 times 10 to the -9th coulombs times Q2, 10 times 10 to the -9th. Again, we do not bring the signs into it. We just use them for qualitative analysis. And divide that by the radius squared. There's the radius, 0.01 meters squared. All right, so we can calculate that out. And that equals 0.009. All right, so our electrostatic force, our force due to the charged particles, is going to be 0.009 newtons, okay, in the upwards direction. So now we got to look at mg and see if that is more or less, because if the electrostatic force is more than the force of gravity, it'll hop up. So m times g is 15 times 10 to the -6 for the mass times g, 9.806. And if you do that, you get 15 times 10 to the -6 times 9.806. You get 1.471 times 10 to the -4th. That's 0.0001. So the force of the particle, call that force electric, is greater than the force of gravity. So will the glass bead leap up? If the force of the electric field is, or the force of the electric particle is greater than the force of gravity, it will, and it is. So yes, it does jump up. All right, so those are all of the examples. I feel like we've covered a lot today, more mathematically than conceptually. If there are any mathematical gaps that you're experiencing, something you don't know how to do, please let me know. You can also YouTube, look up how to add vectors, how to add forces, that kind of stuff. And there's some great videos out there that'll help you out. I'll probably post some on the website as well. So let me know if you have any trouble. There is a homework for this. It's 9 or 10 questions long, plus 2 bonus questions that are mathematically a lot more difficult. You're welcome to try those, but I'll only be grading the first however many, 9 or 10, whatever it says before bonus challenge problems. So get started on those and let me know if you got any questions.